Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Anas bin Sulaiman, and now I want to explain about let assignment 2 for task 1 continuous time for a series on question 3. So the question asks to evaluate the continuous time for a series coefficients of HT signal CK up to 5 harmonic. First, we start with a periodic system where the fundamental period t equals 7, which gives us a fundamental frequency omega naught equal to pi over 7. The given signal xt is an aperiodic pulse with an amplitude of negative 1.5 lasting from t equals 0 to t equal 2. Our target signal is ht equal to negative 4x multiply t over 2 minus 2. By adding 2 to both sides and multiplying by 2 with using time scaling and shifting rules, we find that the original bounds of 0 to 2 will shift to 4 to 8. Since the system repeats every 7 seconds, the interval from 7 to 8 wraps around to become 0 to 1. So the new amplitude we get is ht equal negative 4 multiply negative 1.5 equal to 6. And the ht function will generate and 6 for 0 less than equal t less than 1, and for less than equal t less than 7. And for 0, 1 less than equal t less than 4. Next, we want to evaluate the Fourier coefficient using the standard analysis equation. For the higher harmonics, when k not equal to 0, we integrate this function 6 exponent to the power of negative jk omega naught t. So we can simplify the function using omega naught equal to pi over 7. And also we can apply Euler's, and the value that we get is equal to 1. So after we simplify the function, and the final expression for ck that we get is equal to 3j over k by multiply exponent to the power of negative j 2k pi over 7 minus exponent to the power of negative j 8k pi over 7. Then I will explain how we evaluate the specific harmonics from K1 to K5 to find the absolute magnitude and phase angle in the radian. So, for the first term, we must use Euler identity after we get this function exponent to the power of negative. So we convert it to cos minus j sine to both terms, and we get the approximate value for both. And then we subtract two terms to get one term. So after that, we can multiply with 3 over pi that we calculate to the value of 0.9549 j. And after we multiply, we get the value 1.4557 j minus 1.1609 j squared. And the j squared, we convert it to negative 1, refer to identity, and we get the C1 expression is 1.1609 plus 1.4557 j. After that, we want to find the magnitude value, we must use the formula theorem Pythagoras, and we calculate it to get the final answer for magnitude of C1 is 1.8619. And the phase angle of C1, the value we get after we use this formula, tangent to the power of -1, then the final answer is 0.8976 radian. For the C2, the calculation and method also the same as C1. We must use Euler identity and subtract two terms and multiply with 3 over 2 pi to get C2 equation. So to find the magnitude, we get for C2 magnitude is 0.4144 and the phase angle for C2 is -1.3464 radian. The C3 also same method as well, and we get the magnitude of C3 is 0.4977 and the phase angle for C3 is -0.4489 radian. But for the fourth term and fifth term, they are slightly different. Even though we use Euler identity in that calculation, but after we find the answer for magnitude, we got two negative value for C4, which is -0.3363 minus 0.1620 J. So to find the magnitude value, after we must include this -1 to both sides and we get 0.373. But the critical part here is on the phase angle where the value must be subtract with pi because the level of quadrant. So we get -2.6927 radian. So the final answer is the magnitude is 0.3733 while the phase angle is -2.6927. And then for the last one, C5 also same as well with C4. We must find the magnitude and the phase angle is must to subtract with pi. And then we get -1.7956 radian and the magnitude is 0.1658. So last but not least, the graph of the magnitude spectrum and phase spectrum also shows the almost same result as MATLAB. The value are maybe slightly different, but the shape of the graph is almost same with the manually calculation. That's all from me. Thank you.
Assalamualaikum. My name is Muhammad AMAR HAFIZIN bin HASBULLAH, and I will be covering about the MATLAB task. Okay, so first of all, at line 3, we have t equals to 7, which define the fundamental period of the signal. Then line 4, we have W0 equals to 2 multiplied by pi over t, which computes the fundamental angular of frequency. At line 5, which is k equals to -10 to 9, okay, this one is the ratio of -10 to smaller than 10, basically. So I take 9. Okay, so it specifies the range of Fourier series harmonics to be evaluated from -10 to 9. Okay, as for the time axis, we have t plot line space -7 to 14 seconds. Okay, this is at line 8. Okay, so this is the time vector, which is -7 to 14 seconds. As for the 5,000 points here, so this basically provides high resolution for accurate numerical integration and smooth plot. Okay, next, uh, we move to line 22. Okay, so basically, okay, so line 14 here shows the time dimensional. Okay, so this one, time dimensional HD. Okay, okay, so we move to line 22, which which is T period line space 2 to 9 seconds, and then 5,000. Okay, so this basically isolates the 7-second window, which is from T equals to 2 to 9 seconds. This specific code, which is to ensure the path from 4 to 8 seconds is completely captured. Okay, this one, line 22 until line 23. Okay, next one, we move to line here, line 26. Okay, n equals to 1, line k. This one, line 26 and then line 27. Okay, basically this is the loop that goes through harmonic level of k, which multiplies the signal by the complex exponential formula that uses traps. Here, traps. This code here, traps. So basically the trap function is to calculate the Fourier coefficients, which is ck, through numerical integration. Okay, so next one, we move to line 30, which is ck apps ck. So basically this line basically remove the errors. It will force the value into 10 the power of -4 to 0. Okay, to avoid any messy and spiky graph. Okay, and I will show next. Okay, so next one, we move to the line 35 and then line 36 and then line 43. Okay, this is where the panel 1 and panel 2. This is where the uh, magnitude spectrum and phase spectrum graph will be used in the code. Okay, so this subplot and stem here, FCK. So basically this splits the results of the graph into two stack graph. Okay, I will show. Okay, so this one, this is the magnitude spectrum and then this is the phase spectrum. Okay, so basically because we know the Fourier itself is coefficients to the complex numbers, right? So they need to be separate so that it is easy to see. Okay, so this is the magnitude spectrum and then this is the phase spectrum. Okay, as for the last function of the code, which is here at line 52, for n equals to 1 line k. Okay, so this basically will show and then print table of result. Okay, this one. So we can map it through our hand calculation. Okay, so this one, this is the command window here for line 52 here. We show him. Okay, so I will show the graph again. So this figure 1 is the time dimensional HT, and then figure 2 is the CTFS of magnitude spectrum and CTFS of phase spectrum. So that is all from MATLAB, and thank you for listening. Okay, Assalamualaikum.
Today, we will explain the expression of S1 simulation. We will explore how this is a transition between the time for considerment using the popular of Fourier theory and system synthesis. To begin with, we will establish the envelope and define the term of a signal, which is t equal to 7 uh, is sets the millimeter of the second omega 0 to 2 pi of q calculate c 0 and q equal to 10 to 9 specifies the harmonic range it as 20 c indicates in size to protein. So the analysis process is a complex and standard signal to its individual pure frequency component, which answers the question what the signal atmosphere and how strong of shift it is each component. So so the headings that third scale is equal to n. So the headings is exactly one complete single period 7 from t equal to 2 and to t equal to 9 our pulse wave where it has an amplitude of 6 between t equal to 4 and t equal to 8. Uh, CK, CK0s are liquid and MTL, black frequency spectrum wave. The for loop is our analysis engine. It's looked through each harmonic index A and use numerical trapezoidal multiplication that's to multiply our time signal each period by using computational exponentially 1 to qn omega 0 over that single 1 period. The synthesis is the exact opposite of our analysis. Instead of decomposing signal frequency, synthesis take frequency of comments and cross time to build a or reconstruct a time domain. Instead of running a summation group of CK generic data, the time domain baseline directly cosmetically is a logic definition. So baseline or establish of the periodic time domains in null profile HD from T equal to -7 to 40. In the context, this is the ideal benchmark signal that a synthesis process aim to achieve. Its layout exact physical shape of the elliptic square wave in time. So the visual representation of the signal showing as time signal for generic by this method, keep age line by 2. So the graph display the ideal periodic square wave running a cycle is represent the complete synthesis wave shape that shown in the time graph. Next, we show the graph result. This was the time signal for synthesis using the square wave, and this is the magnetic spectrum CPF as in this the graph for the analysis by frequency going up and then down, having the same amplitude. For this one is sine wave, but the wave is not really clean, but you still can see how the graph is result. So to summarize, using only our analysis calculate our analysis calculate in, our analysis calculating the frequency spectrum plate CK from our isolated period plot line. Our our synthesis target by mapping out how the signal behave magnetically across continuous time. Together, they showcase both sides of the continuous period time series as a FAHMI